Let us have an example. A virtual image cannot be caught on a screen, but we see our image in a plane mirror, which is a virtual image. Let us have the solution. It is true that a plane mirror forms a virtual image, but our eye consists of a convex lens and the virtual image formed by the mirror acts as an object for this lens. The convex lens of our eye then focuses the image on retina, which we are able to see. Let us have another example. A beam of light converges at a point P. Now a lens is placed in the path of the converged beam 12 cm from P. At what point does the beam converge if the lens is A convex lens of focal length 20 cm and B. A concave lens of focal length 16 cm. Let us have the solution. In the given situation, the object is virtual and the image formed is real. Object distance u is equal to plus 12 centimeters. Let us take the case in which a convex lens is placed in between. Focal length of the convex lens f equals 20 centimeters. Let the image distance be v. According to the lens formula, we have the relation 1 by v minus 1 by u is equal to 1 by f. On substituting u and f, we get v is equal to 7.5 centimeters. Hence, the image is formed 7.5 centimeter away from the lens toward its right. Let us consider the second case in which a concave lens is placed in between. Focal length of the concave lens f equals minus 16 centimeters. Let the image distance be v. According to the lens formula, we have the relation 1 by v minus 1 by u is equal to 1 by f. On substituting u and f, we get v is equal to 48 centimeters. Therefore, we have the image distance v is equal to 48 centimeters away from the lens toward its right. Let us have an example over compound microscope. A compound microscope consists of an objective lens of focal length 2 cm and an eyepiece of focal length 6.25 cm separated by a distance of 15 cm. How far from the objective should an object be placed in order to obtain the final image at A, the least distance of distinct vision 25 cm, and B at infinity? What is the magnifying power of the microscope in each case? Let us have the solution. Focal length of the objective lens is given to be 2 cm. Focal length of the eyepiece is given to be 6.25 cm. And distance between the objective lens and the eyepiece is given to be 15 cm. Let us consider the case 1. Least distance of distinct vision d is equal to 25 centimeters. Therefore, image distance for the eyepiece v2 is equal to minus 25 centimeters. Object distance for the eyepiece is equal to u2. According to the lens formula, we have the relation 1 by v2 minus 1 by u2 is equal to 1 by f2. On substituting v2 and f2, we have u2 is equal to minus 5 centimeters. Image distance for the objective lens equals v1, which equals d plus u2. This implies image distance equals 10 centimeters. Object distance for the objective lens equals u1. According to the lens formula, we have the relation 1 by v1 minus 1 by u1 is equal to 1 by f1. Therefore, on substituting v1 and f1, we have u1 is equal to minus 2.5 centimeters. Therefore, magnitude of the object distance u1 is equal to 2.5 centimeters. The magnifying power of a compound microscope is given by the relation m is equal to v1 by magnitude of u1 into 1 plus d prime by f2. On substituting v1 u1, d prime and f2, we have magnification is equal to 20. Hence, the magnifying power of the microscope is 20. Let us consider the second case, in which the final image is formed at infinity. We have image distance for the eyepiece, that is v2 at infinity. Object distance for the eyepiece is u2. According to the lens formula, we have the relation 1 by v2 minus 1 by u2 is equal to 1 by f2. Therefore, u2 is equal to minus 6.25 centimeters. Now, image distance for the objective lens v1 is equal to d plus u2, which equals 8.75 centimeters. Object distance for the objective lens is equal to u1. According to the lens formula, we have the relation 1 by v1 minus 1 by u1 is equal to 1 by f1. On substituting v1 and f1, we have the object distance is equal to minus 2.59 centimeters. Hence, the magnitude of the object distance will be equal to 2.59 centimeters. The magnifying power of a compound microscope is given by the relation m is equal to v1 by modulus of u1 into d prime divided by modulus of u2, which equals 8.75 divided by 2.59 into 25 divided by 6.25, which equals 13.51. Hence, the magnifying power of the microscope is 13.51. Let us have an example over the telescope. First part. A giant refracting telescope at an observatory has an objective lens of focal length 15 meters. If an eyepiece of focal length 1 centimeter is used, what is the angular magnification of the telescope? Second part. If this telescope is used to view the moon, what is the diameter of the image of the moon formed by the objective lens? The diameter of moon is 3.48 into 10 to the power 6 meters and the radius of lunar orbit is 3.8 into 10 to the power 8 meters. Let us have the solution. Focal length of the objective lens is f0, which equals 15 meters, which equals 15 into 10 to the power 2 centimeters. Focal length of the eyepiece fe equals 1 centimeters. Let us consider the first case. The angular magnification of a telescope is given as alpha is equal to f0 by fe. Therefore, alpha is equal to 1500. Hence, the angular magnification of the given refracting telescope is 1500. We know that the diameter of the moon is given by d equals 3.48 into 10 to the power 6 meters and radius of the lunar orbit given by r0 is 3.8 into 10 to the power 8 meters. Let d prime be the diameter of the image of the moon formed by the objective lens. Then the angle subtended by the diameter of the moon is equal to the angle subtended by the image. We have d by r0 is equal to d prime by f0. On substituting the values, we have 3.48 into 10 to the power 6 divided by 3.8 into 10 to the power 8 is equal to d prime by 15. Therefore, d prime equals 13.74 centimeters. Hence, the diameter of the moon's image formed by the objective lens is 13.74 centimeters. Let us have another example. A screen is placed 90 cm from an object. The image of the object on the screen is formed by a convex lens at two different locations separated by 20 centimeters. Determine the focal length of the lens. Let us have the solution. Distance between the image, that is screen, and the object given by capital D equals 90 centimeters, and distance between the two locations of the convex lens given by small d equals 20 centimeters. Let the focal length of the lens be f. Focal length is related to small d and d as f is equal to capital D square minus small d square divided by 4d. On substituting the values of capital D and small d, we have the focal length equals 21.39 centimeters. Therefore, the focal length of the convex lens is 21.39 centimeters. Let us have another example. A myopic person has been using spectacles of power -1 diopter for distant vision. During old age, he also needs to use separate reading glass of power of 2 diopters. Explain what may have happened. Let us have the solution. The power of the spectacles used by the myopic person is -1 diopter. Let us calculate the focal length of the spectacles. Focal length f equals -100 centimeters. Hence, the far point of the person is 100 centimeters. He might have a normal near point of 25 centimeters. When he uses the spectacles, the objects placed at infinity produce virtual images at 100 centimeter. He uses the ability of accommodation of the eye lens to see the objects placed between 100 centimeter and 25 centimeter. During old age, the person uses reading glasses of power P prime is equal to +2 diopters. The ability of accommodation is lost in the old age. This defect is called presbyopia. As a result, he is unable to see clearly the objects placed at 25 centimeters.